everyone. In the previous class, we discussed the application of Terzaghis rock load theory in the design of underground excavations. To continue with the discussion, today we will take up another rock mass classification system, that is rock mass rating. We call it in short as RMR, and we will see that how the application of RMR happens in case of the underground excavations. So, you all know about this table. This we have discussed in some of the earlier classes as well. So, based upon the classification system RMR, we can classify the rocks as has been mentioned in this row. Accordingly, we can assign the rock mass to be very good, good, fair, poor or very poor. So, based upon this classification of rock mass, we can assign some engineering properties to the rock mass. Some of these include the average stand up time, cohesion of rock mass, angle of internal friction of rock mass, allowable bearing pressure and safe cut slope. So, let us discuss these one by one. As I mentioned, the applications of RMR include average stand up time for an arched roof, then cohesion and angle of internal friction, modulus of deformation, allowable bearing pressure in case if you have the foundation to be resting on the rock mass, then we need to design it using this information about the allowable bearing pressure. So, there this application comes into picture. Then shear strength of rock masses and of course, the estimation of support pressure. So, first let us take the average stand up time for an arched roof. So, first we understand that what do we mean by the stand up time. Stand up time is the time through which the tunnel can stand on its own or the excavation can stand on its own without the provision of any support system. So, in case if the stand up time is more, we have little more time for the installation of support system after the excavation. But if the stand up time is low, which will happen in case of the poor rock masses, then in that case the time for the installation of the support system is extremely low, and then we have to do proper planning in order to take care of such a situation. So, this stand up time, it basically depends upon an effective or unsupported span of opening, which is defined as the width of the opening or distance between the tunnel face and the last support, whichever is smaller, whether the width of the opening is smaller or the distance between tunnel face and the last support is small. The stand up time for the arched opening is much larger as compared to the stand up time for the flat roof. So, how it looks like? So, one excavation is like this, it has the arched roof, and another excavation is like this, which has the flat roof. So, in this case the stand up time will be much larger as compared to the stand up time in case of a flat roof. If we go for the controlled blasting, this further enhances the stand up time, because with the controlled blasting we can reduce the damage to the rock mass as compared to random blasting. So, let us come back to this table again and focus only on serial number 2, which gives us the idea about the average stand up time. So, in case if the rock class as per RMR is very good, then the average stand up time is 20 years for 15 meters of span. That means 15 meter of span of the excavation can stand on its own for 20 years. So, this is this is so high because the rock mass rating for this type of rock is pretty high, varying between 81 to 100, resulting in the classification of rock mass as very good. Coming to the next category, that is in case if you have the rock mass as good rock mass, then it is 1 year for 10 meter of span. In case if it is fair quality rock mass, it is 1 week for 5 meter span, and so on. It keeps on reducing, the stand up time keeps on reducing along with the unsupported span length as well. So in case of the poor rock, it is minimum, which is 30 minutes for just 1 meter of span. Now one thing you need to keep in mind, that although let us take for example the fair type of rock mass. So although the average stand up time is 1 week for 5 meter span, but we should not wait till the 6th day and then only go for the installation of support system on the 7th day, because what happens is during those 6 days the rock mass quality further deteriorates. So in case if you have the sufficient stand up time, you should try to provide the support system as soon as possible. So this was about the magnitude of average stand up time for an arched roof. Now various studies were conducted, and based upon that the stand up time versus unsupported span for various rock classes as per RMR was plotted. So here on the x axis you have the stand up time in hour, this is on the log scale, and on y axis you have the unsupported span of the excavation, this is also in the log scale. So you can see that there is a limit of applicability which is shown by this upper portion of this shaded zone. Below this you have the zone where you don't need to provide any support system, and above this you have the situation of immediate collapse. So these dotted lines, they represent the RMR. So this is for RMR 20, this is 30, 40, this is for 50, 60, 70, 80 and 90 and above. So based upon the RMR value, we can find out that what will be the stand up time corresponding to any unsupported span of the opening. We can use this particular figure for the same. As I mentioned that there should not be unnecessary delay in supporting the roof in a rock mass, even though it has high stand up time. So this is a big no. So this may lead to the deterioration in rock mass, which ultimately reduces the stand up time. So what this research worker mentioned, that stand up time improves by one class of RMR value in the excavation which were made by tunnel boring machines. So we have seen that if we go for the controlled blasting as compared to the random blasting, in case of the controlled blasting, the damage to the neighboring rock mass is low, but in case of the excavation which were done by tunnel boring machine, even the disturbance is even lower, and hence the stand up time improves by one class of RMR value. So now coming to the next application, which is cohesion and angle of internal friction. So you need to focus now on serial number 3 and serial number 4. So the first one focuses on the cohesion of the rock mass, and the second one is angle of internal friction. So here see how as the quality of the rock mass deteriorates in terms of RMR reduction in this direction, see how the cohesion of the rock mass also reduces. So for the very good quality rock mass, the cohesion is 0.0 4 MPa and more than that. And in case of the good quality, it is between 0.3 to 0.4 megapascal. But in case if you have very poor quality rock mass, the cohesion of the rock mass is as low as less than 0.1 megapascal. Similar is the situation with reference to angle of internal friction of the rock mass. See how this angle is varying from more than 45° to less than 15° as the rock mass classification changes from very good to very poor. You need to keep in mind that here we are talking in terms of only peak failure values and not the residual one. You all know that when we go for the strength test, shear strength test, we have one as the peak failure, another point as the residual one. So here we are talking with reference to peak failure values. Cohesion is small under low normal stresses due to the rotation of rock blocks. Now RMR along the failure surface may be much less than on the slopes in distress. As far as cohesion in tunnels are concerned, they can be one order higher than slopes because joints are relatively discontinuous, tight and widely spaced in case of the tunnels. Coming to the next category, that is modulus of deformation. So, we have discussed this earlier, that how to determine the modulus of deformation. So, these are obtained from the loading cycle of uniaxial jacking test, whereas the elastic modulus is obtained from the unloading cycle. So, basically when we determine the modulus of deformation, it is the linear and the non-linear part of the loading cycle, both is to be considered for the determination of modulus of deformation. Then we define another quantity which is modulus reduction factor, we call it in short as MRF, which is the ratio of modulus of deformation of rock mass to the elastic modulus of rock material which is obtained from the core. When I say obtained from the core means that the test which is conducted on the intact rock specimen. So, here is a relationship that was given by these research workers between RMR and MRF. RMR is rock mass rating, which is plotted on x-axis, and MRF is modulus reduction factor. I just now defined it, and this is plotted on y-axis. So, from here, corresponding to any value of rock mass rating, we can determine that what is the modulus reduction factor. Once we know the modulus reduction factor, we can find out from this expression, that is MRF is equal to ED upon ER. So, from here we can find out ED as MRF into ER. So, basically this modulus of deformation ED is a product of MRF corresponding to a given RMR value and the elastic modulus of rock material, which is represented as ER. Now, how this plot was developed? So, various cases related to Indian condition and abroad were plotted on the same space, that is MRF versus RMR, and these points which are shown here, these represent the legends for the situation for Kotli Dam, India. Then the circular one is Tehri Dam, India, and then the square one, these represent the cases of Binyavsky. So, basically they tried to derive a relationship between the modulus reduction factor and RMR in general, and then they tried to suggest that how we can determine the modulus of deformation using this RMR. There are few empirical correlations which are also available. So, modulus of deformation as per Beniawski in 1978 is equal to 2 RMR minus 100 and the unit is GPa. We need to be careful about the units because here we are dealing with the empirical correlations. Now this correlation is applicable when the rock mass has RMR greater than 50. In 1983, another empirical correlation was given by Serafim and Pereira, and this is one of the most commonly adopted, commonly used empirical correlations, where the modulus of deformation is given as 10 to the power RMR minus 10 by 40. Again, the unit here is GPa, and this is applicable for all values of RMR. So please remember, these are some simple expressions where if you have the rock mass rating of the rock mass, then you can get the idea about the modulus of deformation of the rock mass. Now if you plot all the data points derived from these two empirical correlations, this is what is the curve looks like in the space, that is in situ modulus deformation versus the RMR. So this has been adopted from this reference which I gave you in the first class only. So here the circular points, they are representing the outcome of the curve ED equal to 10 to the power RMR minus 10 by 40, and the plus sign, which are these signs, they represent the modulus of deformation and the RMR relationship as per this equation, that is ED equal to 2 RMR minus 100. Another correlation which was given by Verman in 1993. So this was applicable for the modulus of deformation of a dry and weak rock mass which has the UCS of the rock as less than 100 MPa around the underground opening and located at the depths exceeding 50 meters. So it was dependent upon the confining pressure due to the overburden, and they came out with this expression where this alpha was 0.16 to 0.3 and it will be higher for poor rocks. So that means if there are two values of alpha, let us say that is 0.18 and another one is say 0.25. So which one will be poor as compared to the other one? It will be this which has the higher value of alpha. And HB, the depth of location under consideration below the ground surface, or we can call this as the overburden depth, and that should be more than 50 meters. So these empirical correlations which are developed on the basis of various test results, the observations in the field, they cannot be used in general for all type of situation. The reason being that these have been developed for particular situation and therefore their applicability also becomes to those type of situations. Coming to the next category, which is related to allowable bearing pressure. So now you need to focus on the serial number 5. You know that when we have any foundation, the foundation should be safe in shear as well as in case of the settlement. The settlement should be within the permissible limit. Now there are many situations where the foundation may be safe in shear but fails in settlement. So in such situation, it is the settlement criteria which governs the bearing capacity of the foundation, and therefore we call that as allowable bearing pressure. So here we are talking about the allowable bearing pressure in ton per meter square corresponding to 12 mm of foundation settlement. So these are related to 12 mm of foundation settlement. Please remember this. So for the case of the rock class 1, 2, 5, see how the range of allowable bearing pressure varies. In case of the very good quality rock mass, the allowable bearing pressure varies between 440 ton per meter square to 600 ton per meter square. However, in case of the very poor quality, it is as low as 30 to 45 ton per meter square. So, as the quality of the rock mass degrades with the reduction in the value of RMR, there is going to be the reduction in the allowable bearing pressure of the footing as well. Coming to the next category, which is the support pressure, that is extremely important with reference to the underground excavation. So, this Unal in 1983, he conducted lot of studies on coal mines, and then he recommended the use of RMR for openings with flat roof, and he mentioned that the vertical support pressure can be defined as 100 minus RMR upon 100 into gamma times B, where this PV is the support pressure, gamma be the unit weight of rock, and B is the tunnel width. Later studies which were conducted afterwards, they mentioned that this equation cannot be used for the rock tunnels with arched roofs, or they cannot be used in squeezing ground conditions. So, as I mentioned that since this is also based upon the studies on coal mines for openings with flat roofs, so it has its limitation as far as the application is concerned. What are the various guidelines for the selection of tunnel supports then? So, we are going to discuss some of these guidelines which were given by Binyavsky in 1984. So, these depend upon the factors such as depth below the surface, tunnel size and shape, and also the method of excavation, whether we had gone for the full face excavation or benching and heading or any other thing. So, let us take a look according to the various rock classes, how the excavation is done and what all are the supports which are recommended. So, here in this table, this has been given in detail that when we have the rock mass class as very good rock having RMR varying between 81 to 100, and the excavation is done as full face and only 3 meter in advance. So, when I say full face means the whole excavation is done in one go, and unsupported length of the excavation can be 3 meters. So, in one go you have the excavation as 3 meter only. So, in this case various support systems have been listed in this table. These include rock bolts, conventional shotcrete and steel sets. In some of the earlier classes I showed you some of the pictures of these supports. So, now you should be able to connect that what I am discussing with you. So, generally in this case no support is required except for occasional spot bolting. But in case if we have the good rock with RMR varying between 61 to 80, we go for the full face excavation, and of course here the quality has deteriorated from this class to this class. So, the advance is also reduced, you see. Tunnel advance is also reduced to 1 to 1.5 meter. So, the complete support 20 meter from the face. In this case, in case if you have the rock bolts which are 20 meter diameter and fully grouted, locally bolts in the crown portion of the tunnel which are 3 meter long should be provided. These are spaced at 2.5 meter with occasional wire mesh. Then in case you want to go for conventional shotcreting, then 50 millimeter should be the thickness of the shotcrete in crown portion wherever it is required, and you don't need to go for the steel sets. In case if you have the fair rock where the RMR varies between 41 to 100, one needs to go for the excavation as heading and benching, and one can advance 1.5 to 3 meter in heading, and one should commence the installation of the support system after each blast. So, complete support should be 10 meter from the face. So, in this case, if you have the rock bolts, so systematic bolts 4-meter long should be provided, which should be spaced 1.5 to 2 meter in crown and walls with wire mesh in crown. That is also needed here. In case of the conventional shotcrete, it is the 50 to 100 millimeter thickness of the shotcrete should be provided in the crown portion and 30 thick in the sides. So, this is about rock bolts and the shotcrete, and as far as the steel sets are concerned, they are not needed. But in case if you have the poor rock with RMR varying between 21 to 40, you see that you may go for light to medium steel ribs which are spaced 1.5 meter wherever required. So, in this case, the top heading and benching method of excavation is adopted with the 1 to 1.5 meter advance in the top heading, and one needs to go for the installation of the support system concurrently with excavation 10 meter from the face. Systematic rock bolts of length 4 to 5 meter should be installed. These are spaced 1 to 1.5 meter in the crown portion and wall with the wire mesh. As far as the conventional shotcrete is concerned, one needs to provide 100 to 150 thick shotcrete layer in the crown portion and 100 millimeter thick shotcrete layer in the side walls of the tunnel. In case if you have very poor rock where RMR is less than 20, then one needs to go for the multiple drift method. Please, right now you just learn about some of these terms related to the method of excavation. Little later I will be explaining you all these methods, that what exactly is the difference between multiple drift method, heading and benching method, full face method, all those things we will be discussing. So, in case if you have the very poor rock mass, one needs to go for the multiple drift method for the excavation and advance only 0.5 to 1.5 meter advance in the top heading. You need to install the support concurrently with the excavation and provision of the shotcrete as soon as possible after the blasting, because what happens is, since it is very poor rock mass, immediately upon the excavation the rock mass starts experiencing the fall of roof wedges or maybe from the side walls. So, if you provide the shotcrete immediately after the blasting, at least it provides some kind of support and prevent this type of failure. In this case, one needs to go for the systematic rock bolts of 5 to 6 meter length, should be spaced 1 to 1.5 meter in crown portion and walls with the wire mesh, and one needs to also provide the bolt invert. For the conventional shotcrete, this is 150 to 200 in the crown portion, 150 in the sides and 50 on the face. As far as the steel sets are concerned, one needs to go for medium to heavy ribs which are spaced 0.75 meter with steel lagging and forepoling if it is required, and you need to go for the close invert. So, as far as the application parts are concerned, we discussed that how we can go for the RMR system to determine the various aspects such as stand up time, then cohesion and angle of internal friction or the shear strength parameters of the rock mass, modulus of deformation, support pressure, and other applications that we just now learned. But then this system has some serious limitations as well. These include that it is very unreliable in case you have very poor rock masses. And then you know how to determine this RMR for the rock mass. We have discussed this in some of the earlier lecture. So, we should be careful that we do not double account for any parameter while evaluating the value of the RMR system. So, in spite of its limitation, this is being used extensively, but then wherever it has the limitation, we need to use our engineering judgment before we find any application with reference to RMR in such situation. So, we learnt today that how the rock mass rating system, that is RMR system, can be applied to obtain some of the aspects related to the design of underground excavations. So, in the next class we will learn about the application of another classification system, that is Q system, but then first we will learn about some of the tunnel hazards and then we will try to connect the same to the Q system. Thank you very much.